Imagine, you just landed on Mars, you've survived the 7-month journey, you've taken your first steps on another planet, humanity's greatest achievement, and then you realize you may never be able to leave. This is not science fiction. This is not a nightmare scenario invented for a movie. This is what researchers at some of the world's leading space medicine institutions have concluded. After running the numbers, not once, but across dozens of independent studies, the return trip from Mars, the part no one talks about, may be the most dangerous journey in human history. And the physics involved might actually make it impossible. Stay with me, because what comes next will change how you think about space exploration forever. For decades, the dream has been simple: get to Mars. Elon Musk talks about it, NASA plans for it, films are made about it. But here's the question nobody asks out loud. What happens after? Getting to Mars takes about 7 months. You'd spend somewhere between 18 and 26 months on the surface, waiting for the planets to realign for a return window. And then you need to go home. That's another 7 months. Total mission time, roughly 3 years, in space, on a planet with no atmosphere to speak of, no magnetic field to protect you, and gravity you've never trained for. So here's the open question, the one that will hang over this entire video. Is the human body even capable of surviving a round trip to Mars? And if not, would we send people anyway? Let's start with the thing that kills quietly. Radiation. On Earth, our planet's magnetic field acts like an invisible shield, deflecting the most dangerous particles fired at us by the Sun and the wider galaxy. On Mars, that shield is essentially gone. The planet's magnetic field collapsed billions of years ago, and in the space between here and there, you have nothing. NASA's own data from the Curiosity rover measured radiation levels on the surface of Mars, equivalent to receiving a full-body CT scan every 5 to 6 days. Over a 3-year mission, that adds up to more than 600 of those CT scans, back to back, with no recovery time in between. That's enough to raise their lifetime cancer risk by approximately 5%, and that's assuming nothing goes wrong. But here's where it gets strange. Radiation doesn't just increase cancer risk, it affects the brain. Crew members start to forget things, make worse decisions, lose the ability to think clearly under pressure, mid-mission on a planet 300 million kilometers from anyone who could help. Now let's talk about gravity, or rather, the absence of it. 7 months in near weightlessness, what scientists call microgravity, on the way to Mars. The body starts to fall apart. Bones lose density at a rate of roughly 1 to 2% per month in space. Muscle mass dissolves. The heart, which is a muscle, weakens. Fluid shifts toward the head, increasing pressure on the brain and eyes. Astronauts returning from the International Space Station after 6 months can barely walk. Some can't stand unaided, and they've only been in orbit, close to Earth, with rescue available in hours. A Mars crew arrives at the planet after 7 months of physical degradation, and then has to perform complex operations on the surface, in a suit in 38% of Earth's gravity. And this changes everything when you consider the return. Because after 18 months on Mars, adapting to lower gravity, they then spend another 7 months in near zero gravity heading home. The body never truly recovers between these assaults. It simply accumulates damage. But radiation and gravity are only part of the story. Scientists have been tracking a third category of damage, one that accumulates in silence, one that gives no warning until it's too late to act. And it doesn't announce itself on the surface of Mars. It announces itself on the way home. In weightlessness, body fluid that normally stays in the lower half of the body shifts upward, toward the head. Pressure builds inside the skull. It pushes against the optic nerve, the bundle of fibers that connects your eye to your brain. The result? Astronauts who have spent extended time on the International Space Station have come back to Earth with permanently altered vision, not temporarily blurred, permanently changed. Inside NASA, this condition is known as SANS, and they have classified it as a red risk, their highest priority physiological concern for any long-duration mission beyond Earth's orbit. Think about what that means for a crew on the surface of Mars. An astronaut whose vision is deteriorating cannot perform emergency surgery, cannot read instrument panels at full precision, cannot do the things the mission depends on. And then there is a second organ, one whose failure would be just as catastrophic and even harder to detect in time. In 2024, researchers at University College London published the most comprehensive study ever conducted on kidney health during spaceflight. Drawing on data from over 40 missions, humans and animals, and simulations of galactic cosmic radiation equivalent to a full Mars round trip. The conclusion: that radiation causes permanent, irreversible kidney damage, not kidney stones. Structural loss of function. The kidneys stop processing salts and minerals correctly. And here is the detail that should stop you cold. The kidneys are late to show symptoms. The damage accumulates silently, deep inside the mission. By the time it becomes apparent, preventing organ failure may already be impossible. One of the lead researchers put it plainly: an astronaut might make it to Mars, but need dialysis on the way home. And on a spacecraft 300 million kilometers from Earth, there is no dialysis machine. The nearest hospital is 8 months away, on a planet you can no longer reach in time. There is only the crew, the mission, and a body that has been quietly failing for months, without anyone knowing. And all of this, the vision loss, the kidney damage, the brain effects from radiation, happens before the crew even leaves Mars to come home. The return journey, not the outbound trip, not the surface stay, is when a compromised body faces its final test. Because by the time the crew leaves Mars, they are already compromised, weaker, more irradiated, thinking less clearly than the day they arrived, and they still have 7 months to go. So far, we've talked about what happens to the body, but the mission doesn't just take a body to Mars, it takes a person. And humans are social creatures. A message from Earth takes between 3 and 22 minutes to reach Mars, depending on where the planets are in their orbits. A conversation is impossible. You send a message, you wait up to 44 minutes for a response. In an emergency, your crew is entirely alone. Psychological studies of isolated teams in Antarctic research stations, in submarine missions, in simulated Mars habitats show a predictable pattern. Group cohesion collapses around the 8-month mark. Conflict rises. Leadership is challenged. People begin to withdraw. NASA's own HI-SEAS simulation in Hawaii, designed to replicate Mars isolation, saw crews struggle deeply by month 6, and that was on Earth, with rescuers minutes away, with the option to simply walk out. Imagine that same psychological unraveling on a spacecraft with no exit. But here is what the mission planners can't guarantee. Every plan assumes the crew gets home. But getting home from Mars may be the single most complex and fragile thing humanity has ever attempted. And there is one detail buried in the engineering that almost no one outside the research community has fully reckoned with. Every Mars mission plan you've ever heard assumes a return trip. It's built into the architecture, the timelines, the press releases, Elon Musk's Starship architecture, NASA's Moon to Mars program, the Mars Direct plan, all of them build in a return. But some of the most serious scientists working on this problem have quietly begun asking a different question. What if we designed missions that didn't? Not as a death sentence, as a choice. In 2013, a Dutch non-profit called Mars One, now defunct, proposed sending colonists to Mars with no return flight. 100,000 people applied. 100,000 people volunteered to leave Earth forever. And this reveals something uncomfortable about the return problem. The return trip isn't just physically dangerous, it's economically devastating. Bringing humans back from Mars requires launching a rocket from the Martian surface. That rocket needs fuel, and that fuel would have to be produced on Mars itself, extracted from the planet's atmosphere and soil, because carrying enough fuel from Earth for the return trip is simply not feasible. This is theoretically possible, but has never been demonstrated at scale. The fuel production plant would need to arrive on Mars before the crew. It would need to operate reliably for years in Martian conditions. And if it failed, the crew cannot leave. Here is the twist. The return is not a given, it is a gamble. Every Mars mission plan with a return trip has a single point of failure that could strand the entire crew permanently. So, we know what happens to the body. We know what happens to the mind. We know the return is a gamble with no safety net, which means the real question was never about engineering. It was always about something harder than that. The question that makes physicists and ethicists argue in the same room. We've sent humans to dangerous places before. Climbers die on Everest, and others still go. The first sailors who crossed the Atlantic didn't know if they would find anything or fall off the edge of the world. But here's what's different about Mars. We know the risks in advance, not vaguely, in detail. We can measure precisely how much radiation a crew will absorb. We can model the bone density loss. We can predict, almost to the month, when the psychological strain becomes unbearable. We know, with reasonable confidence, that the first crew to go to Mars will come back damaged, possibly unable to walk unaided, possibly with elevated cancer rates, possibly thinking less clearly than the day they left, and some of them may not come back at all. The question is no longer, can we go to Mars? We probably can. The question is, do we have the right to send humans there, knowing what we know? And who decides?